Okay, thank you very much. It is a pleasure to talk in this group. My talk is called the Weyl ambient metric, and it is ongoing work with Weyl and Gia, who is my collaborator from UIUC. And it is based on these three papers here. This paper is a paper by Rob Lee and Luca Ciantelli in 2019. This paper is called the ambient metric by Pfefferman and Graham, and this is our paper published last year. Okay, let me start with the outline of the talk. The talk is going to have basically three parts, roughly. In the first part, I will basically set up the stage by introducing what we mean by Riemannian and conformal geometry. In the second main part, which is the bulk of the talk, will be to explain the ambient construction. And I will do this in two steps. First, I will describe the flat ambient metric, just to get into it. But the most useful generalization is the Ricci-flat ambient metric. And in the last part of the talk, I will basically say what we did, where we basically generalize this a little bit to include what is called the Weyl connection. So I will make a very light review of the Weyl connection, Weyl geometry, and finally I will introduce the Weyl ambient metric. I will end with some outlook. Okay, let's begin. What is Riemannian geometry? In Riemannian geometry, we assume we have some manifold M with some dimension D, and let's assume we have a metric, pseudo-Riemannian or Euclidean signature, doesn't matter. Riemannian geometry is basically the study of quantities that are invariant under diffeomorphisms, or in other words, change of coordinates, which are constructed out of the metric GMN. These quantities are what I'll refer to as Riemann tensors, and are the basic objects that appear in general relativity, as we all know, since the diffeomorphisms group is the fundamental symmetry of the theory. This is a little misplaced. Another fundamental object is, as we all know, is the Levi-Civita connection, which is again constructed out of the metric G. It is a unique solution which is metric compatible with the metric and has zero torsion. And using the Levi-Civita connection, we can construct other tensors. We can construct Riemannian tensors. Perhaps the most important one is the Riemann tensor itself, which basically tells the curvature of the space. And it transforms as 1,3 tensor, since it has one upper and three lower indices. So there is a simple procedure in Riemann geometry to create new tensors out of the Riemann tensor. And we start with the Riemann tensor, and we just hit with an arbitrary number of covariant derivatives. Here, the covariant derivatives, again, the Levi-Civita connection. The simple circle symbolizes the Levi-Civita connection, because we're going to talk about more general connections later on in the talk. But what I have in mind here, we basically have the Riemann tensor. We hit with an arbitrary number of derivatives. What I mean here by this is just this, and so. And we all know this is another Riemannian tensor, so it transforms like a tensor at diffeomorphisms. And of course, we can also take arbitrary contractions with the metric and create new tensors. So there is an infinite number of these tensors we can create. Now, what is conformal geometry? Conformal geometry is the same thing with a slight different symmetry. So again, we assume we have a manifold and a metric, or some people say we have a conformal class of metric, but let's assume we have some manifold dimension D and a metric. And then we want to find quantities that are covariant under both diffeomorphisms, so change of coordinates, as in the Riemannian case, but we also have a new symmetry, which we call the Weyl transformation, which is basically a rescaling of the metric by some function beta, which is a function of position x. So it's not a constant number, a constant dilatation. The power to the -2 here is convention. I use a convention basic by Luca and Rob. It doesn't really matter. All that matters is some function you multiply by the metric. So the group is now not just diffeomorphisms. We have this extra group, which I call the Weyl group. And we need, similar to Riemann geometry, we need to create tensors, which are called conformal tensors, that transform covariantly under both these symmetries. So basically what covariant means is we have some tensor here with some arbitrary number of indices, and under a Weyl transformation transforms to the function to some power Wt times the tensor, where W2 is a real number, and this is called the Weyl weight of the tensor. Okay, so we need to create such tensors. It turns out, though, it's a lot harder to create such, and that such tensors I will call conformal tensors in this talk. Okay, it's generally a lot harder to create such conformal tensors because, for example, if you look at the Ricci scalar under this transformation, it transforms in this complicated way. So you see that it has this function beta, which is I suppress the x dependence, which is power 2 times the Ricci scalar, but all these extra derivatives here. So it is not a conformal tensor, the Ricci scalar. So it's not a good building block for conformal geometry. The main difficulty in a rough sense is that the Levi-Civita connection does not commute with Weyl transformations. Basically, derivatives of this function will appear all over the place. And to ensure that these derivatives cancel, like as you see in the Ricci scalar here, I have these derivatives of the function. To ensure this cancel, all this cancels, so we have a conformal tensor, it's a non-trivial task, and it's not easy to do. Okay, then what are the non-conformal tensors so far? There are not that many. This is not a complete list here that I have, but there are not that many known generally. The most important one is the Weyl tensor, I would say, which is basically the analog of a Riemann tensor for conformal geometry. And it is constructed out of, as you can see, out of the Riemann. And there's some Ricci here combinations, some Ricci scalar and metric. This basically, all this combination ensures this is traceless metric and transforms like a conformal tensor. The Weyl tensor is special because it's a conformal tensor in any dimension. Okay, so it appears all over the place in physics. It appears in trace anomalies, in conformal gravity, and so on. Another known tensor, conformal tensor, that people have found is the cotton tensor. And this here is a formula for it. This P here is what is called the Schouten tensor, and it appears a lot in conformal geometry, but itself is not a conformal tensor, but conformal tensors are constructed out of it. As you can see, the cotton tensor is derivatives of the Schouten tensor. I just want to mention that the conformal tensor, the cotton tensor, sorry, is a conformal tensor only d equals 3. So in 3-dimensional manifolds. If you go to 4 dimensions, it won't be a conformal tensor anymore. So conformal tensors are very sensitive to dimensionality of your space. Finally, in 4 dimensions, there is another known tensor, which is called the Bach tensor. And as you can see, it's a semi-involved formula. It has two covariant derivatives of this Schouten tensor here. By the way, this Schouten tensor here, this is the Ricci tensor, the usual Ricci tensor. Okay, it's defined through the Ricci tensor. And so these formulas are not easy to find, but you can trust in that you can check after you do a Weyl transformation of this form. You can check that all these tensors, at least for d equals 4 the Bach and d equals 3 the cotton, transform covariantly. Generally, in higher dimensions, Pfeffer and Graham gave a generalization which they call obstruction tensors. And will symbolize omega. It's a symmetric traceless tensor. And there is an index k here. For k equals 1, for example, I just have the Bach tensor. So when I set k equals 1, this will be just the Bach tensor that just described. But for k equals 2, for example. I won't describe the formula, it's very complicated, but it will be a conformal tensor in 6D, only 6 dimensions. And so on. For k equals 3, it will be a conformal tensor in 8D. So there is some general definition given by Fermat-Graham, which I'll explain a little bit later, but these are important tensors.
So why do
And
they
also,
only, sorry to interrupt. Is this only in in even dimensions?
yeah, it's only in even dimensions. That's right.
Okay.
So in odd dimensions, I've tried to find, there are some proposals I haven't mentioned here for conformal tensors, but I haven't found them many. And I don't know completely what is known in odd dimensions, but I don't think there's many known tensors.
Is there any deep understanding why this is the case?
I don't have a deep understanding why is the case. There is a deep understanding, a very easy understanding in terms of conformal invariants that can only appear in even dimensions. But here we talk about tensors, so I don't have an understanding why this happens.
Good, thanks.
Yeah, no worries. So the question arises, okay, we can play around and find this tensor, but is there a systematic approach to find this conformal tensor? Similar to...
Just a question.
Sure.
These obstruction tensors are not known in general?
So the way to find them explicitly is you need to solve Einstein's equations. So they are known up to 8D. So the higher dimension you go, the harder it is to solve Einstein's equations. So explicitly, they're not known in all D.
Let me understand this. So is that, for example, in 4D, the obstruction tensor is the Euler density plus the Weyl square. Is that?
Oh, no, so that is a conformal. It's a scalar, right?
It's a scalar. But if I take the derivative of the metric with respect to the metric of this anomaly, I get the Bach tensor.
That's right.
So
That's right.
now if I go to 6D, I know that the anomaly is the Euler density plus a linear combination of Weyl tensors in 6D. Is that the standard thing? And then if I take the derivative, if I take the functional derivative with respect to the metric, I get an obstruction tensor. Is this?
That is right. That's exactly right. And these obstruction tensors are specifically for holographic anomalies. So you take the specific combination of the Weyl contractions. So you take the holographic anomaly, which is a combination of Weyl contractions, and you vary this with a metric, and that will be the obstruction tensor, as originally defined by Fermat-Graham.
I don't think it's only holographic. It's for a general theory.
It doesn't have to be.
Sorry?
It doesn't have to be. It doesn't have to be. I'm just saying that's how they originally defined it.
Okay. Okay. Thanks. So yeah, I needed to understand that.
There is a question that I have on this. For example, what is the complete list? By taking these metric variations, are they all independent or maybe they're dependent? I don't know the answer to that.
Taking the metric variations of the conformal anomalies.
Right.
You mean how many independent conformal tensors you find?
Yes. My impression is that the abstraction tensors will be kind of complete basis, although I haven't explicitly seen it proven. But
this is a good. This is a good point. Yes. Yeah, I don't know.
And these tensors will be basically the analog of Einstein tensor for conformal gravity, right? Because it's the equation of motion. The variation of the action. But anyways, yeah. Should I go on? Yeah. Okay, so what are the systematic approaches besides playing around? There are basically two systematic approaches in the literature. One is called tractor calculus, and the main guy is Rod Gover and his collaborators. And the other approach is the ambient metric approach by Pfefferman and Graham, which I'm going to focus on this talk, on this second approach. I don't know the first approach that much, but they have collaborated, so they kind of are related to approaches. So, okay, so for this talk, we're going to focus on the ambient construction. So what is the ambient construction? In this slide, I'm going to give kind of like a schematic basic idea, and then I'll dive into more details on what it is. So my goal, at least in this slide, is to give you the general idea. So what we have is we have the ambient space. Well, let's say this is a D plus 2 dimensional space. And we will have some hypersurface. Okay, the ambient space will have a metric, GMN, which was simulated by tilde. And we take a hypersurface on this space, and that will induce an induced metric we'll call Hij on this hypersurface. So the construction is sufficiently engineered so that diffeomorphism in the ambient space, or at least some part of diffeomorphism, become Weyl transformations in the submanifold. So basically, we have some kind of diffeomorphism here, where for the submanifold metric, H corresponds to the usual Weyl transformation. And so if we manage to find that, then we can construct Riemann tensors in the ambient space, G tilde. And then by doing, since we know they're Riemannian tensors and we know how they transform under coordinate transformations, we can basically induce some tensor in the submanifold H here, and we'll know how they transform under the Weyl transformation, which is what we're looking for. And the induced tensor will turn out to be conformal tensors constructed out of the induced metric. It turns out, we'll see that explicitly that this hypersurface is a null hypersurface, and that is key. You need to have a null hypersurface. At least this construction has null submanifolds. Okay, so I hope this was, you got the basic idea at hand. Basically, we use diffeomorphism in a bigger space that look like Weyl transformation for a smaller space.
Does this diffeomorphism preserve the subspace? I mean,
it does, yes. It will turn out that it does. That's right.
And the subspace is D-dimensional, or it doesn't matter?
Yeah, so this subspace will be D-dimensional, but the actual conformal manifold will be, sorry, the subspace, as I draw it here, it's D plus 1 dimensional, and that will be a null hypersurface. And the actual, we'll take another slice of that also, will be D-dimensional. So the conformal geometry will be in this codimension 2 submanifold at the end of the day. The D plus 1 dimensional manifold is actually a null surface. So it's, as we'll see, will be the light cone, and I'll describe it in detail on the next slide.
Okay.
Okay. Yeah, thanks. Okay. So I'll start with the flat ambient metric. Just to show in this slide, I want to show basically we're going to use 3 coordinate systems, and I will explain in detail. So we consider the ambient space to be a R1, D plus 1 Minkowski metric. So that means there is only one time-like direction and D plus 1 space-like directions. It's the usual flat metric, no curvature. And we'll start from that, and that will be our ambient metric. The usual inertial coordinate system is this. So I labeled the time-like direction by the x minus 1 coordinate, like that. Maybe I should have done x0, but it doesn't matter. And all the other xi's go from 1 to D plus 1, and they're all space-like. So that's the most familiar coordinate system. Now you can change coordinates and go to the ambient coordinate system, which is described by t, rho, and x. And that's the most important coordinate system for this talk. So I'll explain the coordinates in detail. But basically, yeah, so we'll go to T rho and X, I, and the I go from 1 to D. And back to Padeli's question, that is the codimension 2 submanifold that I was talking about. And the third metric, the third coordinate system is what Pfefferman and Graham call cone form. So I use that word. It looks like the metric on a cone for some reason. And it is given by this. So the reason I'm going to mention this is because that makes contact of the ambient metric with de Sitter spaces. So that makes contact to holography, which I won't describe in detail in this talk. It's beyond the scope of this talk, but that's how I was introduced to this. And that's one of my main motivations, what this means for holography. So just for now, you should know that de Sitter space are embedded also in the ambient space. And we'll see also asymptotically and de Sitter space are also embedded. So there's a connection to holography.
Sorry, Manthos, I have a question, sorry to interrupt, but maybe it's a naive question, but the moment you're fixing the metric to be a Minkowski metric, exactly at this moment you're breaking the diffeomorphism group. So I'm a little bit confused. How can you understand the effect of the diffeomorphism group on the embedding metric? Because you're breaking it. So is it correct?
I don't agree with saying that because of a flat metric I break diffeomorphism.
But the moment you're fixing the metric, the diffeomorphism group is broken, right?
No.
You can describe it with a different coordinate system, right?
Maybe you mean that I have a specific coordinate system? That's why you mean I break it? It's just in this coordinate system, it's expressed like that, but...
A Minkowski metric is a Minkowski metric in any coordinate system, right?
That's what I mean, doesn't break. That's why I say doesn't break.
Okay, good.
But yeah, but if you fix a coordinate, you can say it breaks diffeomorphism, if that's what you mean. But at the end of the day, the real geometry is flat, right? You can describe in a coordinate system.
Yes, with this I agree. Okay, so I'm just trying to understand exactly the meaning of diffeomorphism. Okay, thank you.
Mm-hmm. Yeah. Okay, so I will start by describing these two and a special focus on this, and then I'll describe the cone metric a little bit and see how de Sitters are in this construction. Okay, so this is the slide with the most amount of information, so I'll go slowly, and because I want to, that's I guess the most important slide. So as we said, we started with flat coordinates. Okay. And this will be the time-like direction, x minus 1, and this will be the space-like direction, xy plus 1, no, xi plus 1. Okay, there are d of them. And I wanted to go now to the ambient coordinates and see what they mean in the usual inertial coordinates that we have, so we can have a picture. What it turns out, what happens is that the rho equals 0 hypersurface, the rho equals 0 surface is the null cone, the future null cone. So basically you have the cone here in the future positive x minus 1 direction. And that's exactly described, the surface of this cone is the rho equals 0 in the ambient coordinate system. The t coordinate, so we have rho and t, the t coordinate is radial outwards on the surface of the cone. So this is the t direction. Now I hope you can convince yourselves that if I want to find the metric on the null cone, I just pull it back at rho equals 0. And what you get is the metric is this. So it's t squared times the metric on a d sphere. But remember, the null cone is a d plus 1 dimensional manifold. The ambient is d plus 2, but it has one degenerate direction because one is light-like, right, direction. So the metric is just the d sphere, basically, times some t squared coordinate. Well, the way you can show that is you can plug in here rho equals 0, basically. And we are, the surface of the null cone is described by d rho equals 0. So the one form, sorry, is is the kernel of the one form D rho, to be more precise. Or you can think of this as the rho equals 0 surface. Okay, now, so basically the D sphere is kind of like this. This circle here represents the D sphere. Now, see what happens if I change coordinates from T to T prime, like that. So I take T, and I change to a new coordinate T prime, times some function e to the epsilon.
Sorry, can I ask a question?
Yeah,
In this
great.
construction, how do you label the radius of the two sphere?
So,
is it absorbed in the omega d, for instance, or is it to be perceived something like a coefficient in front of that?
so this d omega d is the unit sphere. So we just define to be has radius 1. But if you can consider the whole thing, then it will change the radius. But this is just radius 1. And this sphere will be described by the xi coordinates. This will be, you can imagine, these are the angles of the sphere, if you want.
So in this construction, I take rho equals 0, then I am on a null cone, and then if I take a fixed t, then I have a two sphere of radius t, right?
That's right, yes, that's correct. I guess in bigger t, you can see the circle becomes bigger, right, in the picture. Thanks for the question. What I want to say, okay, back to the diffeomorphism that I was talking about, that was kind of like, yes.
Sorry, I think this is called the celestial sphere, isn't it?
Yes, that's right. Good point. That's the celestial sphere. If you look at, I guess, the universe. Okay, so let's go back to this diffeomorphism. If you do this diffeomorphism, you just change the t coordinate by some function times t prime. What you can do is you change the metric or describe the same flat metric in this t prime coordinate, and then you pull it back to the null surface. And what happens now is the metric on the null surface has this function e to the 2 epsilon x. Epsilon is an arbitrary function of x. And sorry, and notice this is Weyl transformation. So if we identify, I had before the function beta x, but here you can identify this epsilon x by a log of beta. And it exactly then changes by a Weyl transformation. What changed by Weyl transformation is the pullback metric. Okay, and it came from a diffeomorphism of the ambient metric. And that's what we were looking for. This is very useful, and we'll use this to find conformal tensor. That's the basic idea.
So, can I ask something here? In this construction, it doesn't seem like odd or even dimensionality is any problem, right? It seems like you can choose whatever you want to construct a conformal tensor on a odd dimensionality like subspace, right?
That's true. That's true. So from that perspective, I don't see why even dimensionality is so special compared to it. Yeah.
So the idea is to take a foliation of your null space into spheres, basically.
Yeah, and another way to imagine this, that's true. Another way to imagine what this diffeomorphism does is you take some slices which are wiggly. So you take an arbitrary time-like slice. It will slice the cone on some surface, which has a topology of a sphere, but if you make it wiggly, it won't be a pure sphere anymore.
Right.
It will be actually, right, so.
If you take it
and that's an important one.
If you take it not strictly sphere, but something wiggly, you still have this conformal transformation?
Yeah, exactly right. The induced metric on this wiggly circle will be some function x to the -2 times the d sphere.
Okay, that's interesting.
So it's conformally related to the sphere, by the way I define things. The fact that we get a sphere is the fact which is a flat ambient, and we'll see. I'll see what I mean. We'll generalize this to get any arbitrary background which is not a sphere.
Okay.
A sphere is conformally related to the flat metric, by the way. So anyway, so I will see. No, okay, so we found this diff. Now we wanna remember our goal was to find conformal tensors from ambient Riemann tensors. But since the ambient metric here is flat, we know the Riemann tensor vanishes, right? And that is okay. That is consistent because, as I said just now, for the flat ambient metric, we get the sphere, which is conformally flat. And all conformal tensors for conformal flat backgrounds vanish. So we get 0 from the ambient, but we're supposed to get 0 because the induced metric is just conformally flat. Okay? And that's what I'm saying here. I'm sorry. Okay. And so what we need to do is to generalize this so we don't have conformally flat metrics, just the sphere metric. We just need to have arbitrary metrics. And that is possible. Okay, sorry. Before I make this generalization, let me describe the cone metric that I said. It's the third coordinate system here, this one, because that's important, I guess, for physics, because it connects with holography. And I want to mention it here. Okay, so I'm my bad. So I will do that after the generalization for each flat. Okay, so we had a flat ambient metric. The generalization is just to make it Ricci flat, not just completely flat. So as you can see, we still have the same form of the metric, but the only difference here, instead of the D-sphere, I have an arbitrary metric that depends on both x and rho. But now, instead of, we impose that it must be Ricci flat in the ambient sense. So the ambient Ricci must vanish, or in other words, is a solution of vacuum Einstein's equations. Vacuum Einstein's equations. But again, nothing changes basically to the picture. Rho equals 0 is again a null hypersurface. You can just check this by this metric, from the form of this metric. And the pullback metric now is just t squared, but then you have this, you evaluate this Gij at rho equals 0. That's the pullback metric and then a hypersurface. So I guess this is the rho equals 0, this is the G, and this is the pullback on the null hypersurface. It's t squared times Gij(x) only. The Ricci condition is important. Is actually very important. And one thing it does is you can expand this metric in terms of a Taylor series in rho. And you can use the Ricci equations to propagate away from the null surface. So that's kind of like an initial value problem, what Thanasis talked before. You just imagine this pullback metric to be the initial data, and you propagate at least in the neighborhood near the null surface using the Ricci flatness condition. For example, if I do this series, I can find that G1 is just the 2 times the Skelton tensor, solving Einstein's equation. Yeah. But okay, the more high order you go, the harder it is to do this. And that's what I was talking to Tassos before, in some sense. It's hard to solve Einstein's equation, I guess. We all know that. Even perturbative. Okay, so let me now describe how we get conformal tensors from the ambient Riemann tensors. As we said, this was the ambient form. And it turns out, I will just state some results that are true here. If you calculate the reambient Riemann tensor and you pull it back at the null hypersurface and t equals 1, you just get the Weyl tensor that I said is the most important conformal tensors. If you take one of the components to be rho direction of the ambient Riemann and the other would be JKL, so the JKL are kind of like the induced coordinates, okay, on the codimension 2 hypersurface, by the way. And then it turns out this is just the Cotton tensor. And if you take 2 rho directions in terms of the ambient Riemann and only I and J, and you pull it back, you get the you get the back tensor, which is the 4D conformal tensor. And this is not an accident, okay? And you can prove all this first by brute force. But second, you can prove this is a conformal tensor if you use how the ambient Riemann tensor transforms. So this is the very important proposition that was proven by Pfefferman-Graham. And it says, and let me describe a little bit what it says. It just is basically the transformation law for a tensor. But here I mean the semicolon, I mean covariant derivatives. So this is basically nabla M1, nabla M2, an arbitrary nabla, number of nablas, and you hit on the Riemann tensor, on the ambient Riemann tensor. And when we do this diffeomorphism that I said that actually induce a Weyl transformation, we know how this transforms. And you can prove it transforms like that, where these are kind of like these tensors. These are these matrices here. This has been proven by Pfeffer and Graham, and you can, with this proposition, you can show that all these are indeed transforming like conformal tensors as they should. So the prime here indicates the T prime coordinate system and corresponds to the Weyl transformed metric G prime. Okay, for example, if I set in this proposition here, IJKL, as I said, I get the Weyl Riemann, I get this transformation law. So this proposition just reduces to this and gives me the Weyl weight of the Weyl tensor under conformal transformation. And the same for the Cotton, the same for the Bach. We can solve this. What we did after I generalized this a little bit, we actually were able to generalize this proposition when I introduced the Weyl connection. So okay, to do that, I need to explain a little bit what is the Weyl connection. So I have a slide about this. As I said, conformal transformation is just a metric real scale with a function. Now, for physics, it's very natural to view this as a gauge symmetry, right? Because it's a local symmetry. So what we do, usually we introduce some gauge fields that and construct covariant derivatives out of. So, and so we can create tensors. So here, that's what I'm doing. I indicate a nabla hat, which is the usual, let's say, nabla M some covariant derivative on the base manifold. And I introduce a 1 for M, which is called the Weyl connection. And here, this is the Weyl weight of some tensor, schematically a little bit. So what this covariant derivative does, similar to U1, you can imagine, is that if you have a tensor that transforms like that, then the nabla hat of this tensor also transforms like the tensor. So I can create more Weyl tensors, Weyl covariant tensors by hitting with this nabla hat derivative. Okay, but now this is a little different. This is not conformal geometry anymore. That's why I call it Weyl geometry, because I have introduced a new degree of freedom, right? I don't just rescale the metric, I have also this 1 for main nu. So I call this, the study of these transformations, things that are covariant under this transform, I call this Weyl geometry, okay? Just to distinguish from conformal geometry, where you don't have the same at all. Okay, as for the base connection, what we choose here is a connection that's not metric compatible, and it's actually the nabla M of the metric will be 2A nu, which is A nu is the same Weyl connection, but has zero torsion, and that actually you can solve this equation, and you can find the Weyl connection Christoffel symbols here, which are given here. Okay, and as I mentioned, Weyl geometry is the study of these coordinate transformations. So basically, roughly what happens, you take the Levi-Civita connection, you replace with nabla hat, and now all the tensors become hatted tensors, the Weyl, the Cotton, and the Bach. But an important thing to note is that all these tensors, they will depend not only on the metric, but they will depend on the nu1 form, and will have complicated derivatives. Okay, it will be some function like that. But a nice thing that happens is that these will be Weyl covariant tensors in any dimension, in contrast to these tensors that are only for specific dimension. So it's kind of like a dimensional continuation of these tensors. But in order to do that, to remain the covariance, you need to introduce this gauge field thing. These are just some words. Don't mean that much. Okay, so I was introduced, as I said, ambient construction give us stuff about conformal geometry, systematic way. I was introduced to this topic by a paper by Ciampelli and Lee in 2019, where they introduced this Weyl connection that I just described in holography. And then we had a paper with Gia, with Weyl, which was a follow-up of that paper. And we now working on a generalization of the ambient construction where we introduce basically this one form gauge field in the Weyl ambient, and we can derive tensors in Weyl geometry now. And things work out as smoothly as one could expect. So let me describe a little bit how we arrived at this. We started from this cone form that I described. So here I have some metric. I have this S. Sorry, this should be ds here. There's a typo. And this, imagine for now, this is an arbitrary G metric. So it's kind of like a Kalyuchak line type decomposition, okay, something like that. There's no compact dimension. It turns out that the reach of this metric, G tilde, is just the reach of G. This should be WFG, I'm sorry. So the reach is decomposed like that, in this way. So if the ambient metric is reach flat, then what you get is that this metric, which is, I call here G plus, sorry, satisfies Einstein's equation with its negative cosmological constant. And that's under de Sitter, asymptotically under de Sitter spaces. And that's how the connection with holography comes. What Rob and Luca did, they generalized kind of like the Fefferman-Graham gauge, and they introduced this Weyl connection here, AI. So we took that generalization, and they showed one important result of their paper is that they gave this interpretation of this new extra mode in the metric. The interpretation for the boundary field theory has interpretation of the Weyl connection that I described when you pull it back to the boundary. Okay, so we took that metric, we did the coordinate transformation like that so we took that metric, we plug it in here, and then we did the coordinate transformation like this, and we got what we call the Weyl ambient metric, which has this form. So it's heavily based on their ansatz, okay? So we call this the Weyl ambient metric. And you can see the only difference that this, again, this mode appears, which is the Weyl, which will have the interpretation of the Weyl connection. And just to compare things, we'll start with the...
Mantho, just a second, if you can. So, what is the boundary metric of Ciambelli and Lee? If I do the expansion, I see. Yeah, what is the?
Yeah, so you will expand this gamma ij to some partials in Z, right? Z equals 0 is where the boundary is. And so there will be some terms like that, ij and high order terms. So this is the metric on the boundary, the first term.
Sorry, but isn't it that so the Weyl connection, how does it contribute to the boundary metric?
So what they found is that if you take the ambient connection, right, the connection, the Levi-Civita connection of this thing, and you do a Z expansion, the 0th order, which is supposed to be the pullback in some sense of the Z equals 0, is not just the Levi-Civita connection of this guy, of this. The A nu will come into it, and it will be exactly the Weyl connection, this. You'll get exactly the 0th order, you get this, where this is the Levi-Civita of gamma 0, ij, which is the pullback metric.
So you would say that in the boundary, holographically, you have a boundary metric, which is this gamma ij, but it has a non-trivial, a non-Levi-Civita connection.
That's right. That was their proposal. Yeah. So this is interesting that this happens only for asymptotic boundaries, as far as I know. If you have a boundary which is not asymptotic and you pull it back, you always get Levi-Civita connection, the pullback. But asymptotically, you can get a different connection, which is not the Levi-Civita boundary. That's what they saw, basically.
What is the asymptotics of this spacetime here? Is it flat? Is it ADS?
As it's okay, this WFG is asymptotically ADS. So it does satisfy Einstein's equation with negative cosmological constant.
Okay. So z equals 0 is the ADS boundary here.
Yes, that's right. So you will have z equals 0 here. We'll have gamma ij, which is this. And the bulk is in this direction, the z. And it's asymptotically ADS here, close to the boundary. In the bulk, you can have black holes, you can have any kind of. So what we do is a perturbative expansion close to the boundary. That's the ground.
And sorry, and you can do the perturbative expansion this well, because you have Ricci flatness. That's what you said before, right? Or no?
No. So here, that's for the ambient. This WFG is not the ambient. The ambient is, remember, the ambient is this. This is just this. So this metric just satisfies, is not Ricci flat. It has cosmological constant. The ambient is Ricci flat. These are the same equations in a way. You can derive one from the other if you assume this decomposition. So the ambient is Ricci flat. There is a submanifold which is asymptotically ADS, which has curvature. It's kind of like the hyperboloid, which is the anti-de Sitter space. And there is also the null cone. So all holographies in the ambient is in there, all compactified in a picture, which I can draw.
So let me, sorry, at this point I should have understood it some years ago, but so suppose that the gamma ij is just Minkowski.
Yes.
Do you know of any solution, solution that gives you gamma ij Minkowski and a non-trivial connection? Namely, what could be this very simple situation?
Yes, a good question. I don't know a non-perturbative solution. I was trying to find that. So of course, if this is not there, Minkowski, and you take this to be flat, this was a pure ADS. That's a solution.
This is pure ADS, yes.
If I have this turned on, then, and I put this to be flat at the boundary, you're asking,
Yes.
what is the solution in closed form? I don't have it. I can only solve it perturbatively. So I can find the series expansion series by series, but I don't have a closed solution.
But
so,
okay. From
but it exists, presumably. There is some solution. It's not that it doesn't exist. With a mu turned on. With AI turned on.
Okay, but what is the physics of a system that has lives on a Minkowski space, but it has a non-trivial Weyl connection? Isn't that?
Yeah, that's good. That's an open question as far as I know. We don't really know the physical significance of this connection.
You mean Ciambelli and Lee, they don't know it?
I don't know it. Maybe they do, but I don't know it. I mean, I've been thinking about this, but all I know is geometrically it induced that connection. What does it mean? I can give hypotheses, but they're not very good so far. But this is something I actually want to explore. What does this mean? For fluids and stuff like that. For a fluid band.
Okay, thanks.
Yeah, no problem. Okay, I'm almost out of time. Let me see. Okay, yeah, I just described these are basically a one-to-one correspondence. There's only this new extra field here. The rho equals 0 is an out surface. They're both Ricci flat. We don't change that. The ambient diffeomorphism induced this, as we said, but here we found that they induce this kind of like symmetry of the boundaries. So we have this Weyl symmetry. And we can construct conformal tensors in the ambient. We can construct Weyl covariant tensors using the Weyl ambient. So everything falls through. And what we were able to show is to take this important proposition that I mentioned at Fermat-Graham and prove it for the Weyl ambient, and found how it transforms for the Weyl ambient metric. And I just wanted to notice that this is this kind of like a matrix in the ambient case, and this is the matrix that we get for the Weyl ambient, and this is very simpler. We don't have these terms here; these are 0. So more of them transform very nicely when you reduce the connection, and that's kind of That was nice to get it. And by the way, we used something called WFG diffeomorphisms here, which was also discovered by Rob and Luca in their paper to prove this theorem. And it happens to be the same diffeomorphism, which probably one could expect that. But anyway, I just wanted to mention that. So there is a definition of this abstraction tensor using the ambient Riemann tensor, as I said. That was part of, that's kind of like a good definition of what is this abstraction tensor. Is some component of this ambient Riemann, and then you pull it back. So you take the rho ij rho ambient Riemann, and you take an arbitrary number of rho derivatives, and then you pull back this tensor. And that is what we'll say is the abstraction tensor, and that will be a conformal tensor, and you can prove that. Okay, so we use that as kind of a definition. That's what they used. We just generalize it to describe Valk-covariant abstraction tensor.
So do you find the generalization of the Bach tensor?
Yes, but it's something that will have as an nabla hat. It's a generalization of that, yes, and we'll have the Val connection in it. Yeah, but also for the cotton, there will be a Val cotton. Every tensor will have an analog. No, and the difference is that all this, yeah.
Yeah, I was wondering. So that's so usually in the simplest case, without all this ambient stuff, for example, you take the Ricci scalar and you ask how it transforms under a Weyl transformation, and you find that it gets additional terms that are derivatives of the Weyl, rescaling parameter. You just saw that. So if I do that, so I was wondering if, for example, the simplest abstraction tensor, like the Bach tensor, can be split into a part that is conformal invariant plus something that depends only on the connection, on the non-trivial connection.
Yes, yes, it can. That's true. So let me tell you what I think so it's an interesting thing. So if I take the usual Bach tensor and see how it transforms under G goes to some function times G, I will generally get some function here times Bij plus some derivatives of the log of this function, okay? Just some derivatives of this function. So I will write schematically, this will be d minus 4 times some derivatives of this function that's full conformal covariance. But yes, in d equals 4, this all vanishes, right? So only d equals 4, it's a conformal tensor. Now what happens basically, the rule is you take these derivatives of this function, you replace it with a mu. Because basically you take d of some function, you say this becomes the Weyl connection, but the Weyl connection does not have to be closed, exact, sorry. And that kind of like makes it now to be Weyl covariant in 8 dimension, but you have enlarged the symmetry group. So it's somehow these exact forms that come from derivatives of this function become, become the A mu's as a generalization. Or you can say, if I take A mu to be an exact form, I'll get back to that. That split. So exactness will have a physical meaning, which probably would be the best place to start to see what, if you take a Weyl gauge field that is exact, what does that mean? But I don't know yet what it means. But indeed, that splitting happens.
Okay. Thanks.
Yeah, no problem. And this is the last slide. Okay, these are all geometric construction. I know I'm sorry I haven't talked about physics a lot, but I just want to explain the construction. I hope there will be application for physics later. It's just building the language, right? The tensors, the building blocks. So we believe this will have some application for graphing KFTs where you have a turned on connection and you have this new symmetry as your background symmetry instead of just the usual conformal symmetry that people talk about. As I said, there's a close connection with holography because asymptotically the spaces are embedded in the ambient space. if I want to make a cartoon of this, I will make the Penrose like the conformal compactification of the triangle. Because the ambient is really flat, there is really conformal compactification, and the conformal boundary is null, right? What happens is that basically this kind of surface is where this is asymptotically ADS. This surface here, the null cone, is the rho equals 0 surface that I was talking about. And this point here where they both intersect is the conformal boundary, the z equals 0 in hologram. Okay, obstruction tensors are defined through the ambient Riemann, as I said, and they're basically the building blocks of trace anomalies. That's something I haven't explained, but this is true. We'll think, because I talked about code dimension spaces and all that, we'll think this will have some application for corner symmetries, if you've heard of this, which is code dimension to charges in general relativity. And because we have a null surface, I think this vowel connection is also embedded in Carolian symmetry. I have some ideas about that, but we're still thinking about that. And also, I think there's definitely a connection with holographic renormalization, where instead of introducing counter terms, we kind of introduce topological terms that cancel the divergences. In any case, I think there's a connection with holographic renormalization. And generally, you can take an RG flow. I think a question that I have is, what does this vowel connection mean just for RG flow in general? Because this is like gauging local symmetry, and we know this is very related to RG flow. So maybe you can generalize some RG flow with a vowel connection. And finally, there is some contact with conformal gravity or vowel gravity. I think these tensors are the building blocks for these kind of theories, but I don't know much about them. Okay, thank you very much. Thank you for your attention.
Ωραία, Μάνθο.
So I wasn't over time, because we started later.
Yeah. Can I ask?
Aaron? Yeah.
So why are you using rho equals 0 null cone? Is it essentially, or is it just for simplicity in the expressions? I assume like if you fix rho to some other constant, there is another null cone, right?
No, in this coordinate system, rho equals 0, only rho equals 0 is a null surface in this coordinate system. Because what's posed the nullness is this part of the metric here. If rho is non-zero, you have this dt squared here, and it's not null.
Okay.
But it's specific to the coordinate system. It's not that I think it's any deep, but in this coordinate system, only the rho equals 0 is null.
Okay, thanks. I see.
Basically, the rho is the one that propagates. If you have the null surface, rho is what propagates you beyond the null surface. Which you have worked on stuff like that, right? Like in Savali problems.
Yeah, but it doesn't take you to another null surface, right? That's what you're saying.
Doesn't take me, no. Yeah.
So let me see if I understand well. Like initially you have the ambient metric, and I can see it as a tool to create conformal tensors in any dimension, but they all have the fact that they are like they're zero, the tensors I create, because the ambient metric is flat, right? So now when you
only if you take it flat, right? Only if you take it flat. If you take it Ricci flat, it won't be zero. The Riemann is not zero.
So then when you make the construction with the generalization you worked is the one that you have the Ricci flat, right? And the fact that if you do that, then you are able to create conformal tensors that are non-trivial in that sense, right?
Right. For non-conformal flat backgrounds, yes.
Exactly. And then you can do more, let's say, non-trivial stuff. Like then I can forget about the way I constructed a conformal tensor. I can act like the ambient space is not there, and I can just use the building blocks, the conformal tensors for any, let's say, asymptotically ADS things I want to do in holograph. They can be separate.
Yeah,
They don't have to be connected, right?
That's right. They don't have to be connected. You can view it as kind of like a trick to find
Yeah,
conformal
exactly.
tensor.
Good. Good. Thanks. If there is another question, I have another one.
Yeah. Okay.
So here, when you're saying corners, if I think in terms of the Penrose diagram, so you said it refers to conserved quantities that are in a codimension 2 hypersurface, right? So it should be something like in the intersection of the asymptotic null boundaries.
So
Or
the good thing about the ambient is that this codimension 2 is not asymptotic, it's finite. So the actual codimension 2, the way we find, we say we first pull back to the narrow equals 0, but then we take t equals 1. So we're somewhere here. We're not the conformal at the boundary. I haven't understood that well, but that's true. So that's one of the advantages of the ambient, where you don't have to use asymptotic expansions. It's regular expansion inside.
but
In the usual Pfefferman-Graham gauge, you do asymptotic expansion.
So maybe to make it more specific, for instance, when someone is talking about BMS charges and these things, right? These are quantities that are defined, I guess, in the asymptotic boundary of asymptotic flat spacetimes, I think, like in the future null infinity or past null infinity. But then I guess there is something in this framework. If you were to talk about corners, then it would be at spatial infinity, right?
It won't be at infinity. That's what I'm trying to say. It will be at a finite distance in the bulk. It will be some codimension 2 surface inside.
Okay.
Now, how it's connect to the asymptotic symmetries, I don't know. But there might be a way to connect.
Okay. Good. Thanks.
Yeah. We're not here. That's the space like infinity, right, that you're talking about. We're here for some reason. Are there any other questions?
Yes, maybe. Well, in the standard Pfefferman-Graham story, where there is no Weyl connection, you specify a boundary metric and a boundary energy momentum tensor, as we say it, which means you specify two of the subleading components of this Gij, and then you produce all solutions of Einstein's equations. Here you need to specify also the Weyl connection. Is that an additional degree of freedom?
No. so indeed, the Weyl connection is pure gates, actually. So it's not really, these are the same data, you can find solutions. So the AMU just comes along with the ride, but it plays the role of one connection and make things covariant, but it's not, you don't need it to find a new solution like the A0. It's kind of something that you can probably gauge away by diffeomorphisms, okay, because there is the Pfefferman-Graham theorem. There's probably some diffeomorphisms that gets you to Pfefferman-Graham. So it's not really new data that you need on the boundary. So part of our paper was to use, yeah, sorry, go ahead.
So holographically, then it means that there are no new degrees of freedom in the boundary. Is that the holographic interpretation?
I don't know. It looks like that. At least naively, I would say yes, because you don't need as a new data to solve Einstein's equations. But I'm not sure. I'm not sure if, for example, I'm not sure, for example, okay, maybe that's true for Einstein, but if we have some other bulk which is not Einstein, maybe this is really, maybe this, I don't know. It looks like that because it's pure gauge. So if you're sure about that, this means it's not really nothing new for the boundary. It's just a way to organize things some way, then yes. But yeah, I don't know what it really means for the fluid yet, so that's why I'm not sure what to say, if it's really new degree of freedom or not for the one.
Okay. It's interesting, of course.
I don't know if you know about other works that work with a fluid that has a Weyl connection as a covariant derivative instead of, I don't know if people have done this. But I think probably the Carolean stuff will have special case, this Weyl connection somehow. I think that.
Yeah, this I don't know. I don't know, to be honest, how this connection could be related to the Carolean limit or to the Galilean limit, maybe. Because I think if it is related to one, it should be related to the other. But I think the interesting story is if it can be a genuine new degree of freedom. But I don't know. I wouldn't know how this could come about.
So what I was thinking, if there is a loophole in the Fermat-Graham theorem, but I'm mostly leaning that indeed that is a pure gauge degree of freedom in the bound. It's kind of like the, in a rough sense, like the shift vector, right? We call this pure gauge.
Yes.
In ADM formalism, but so it's kind of like that.
Well, that is why I always thought that it is important to study the simplest case where the boundary metric is just Minkowski, so that you somehow take pure ADS and you just introduce a Weyl connection and see whether this makes any sense. And that's a simple case maybe to study, at least perturbatively. And that is, yeah, that could be interesting. Yeah, I kind of have the feeling that if it is non-trivial, this Weyl connection should be related with having a boundary metric which is not conformally flat. Now, I don't know why I'm saying that, but that's my feeling. If your boundary metric is really flat, like Minkowski, or conformally flat, then it's not clear what is this Weyl connection doing to me. But if it is not conformally flat, yeah. Anyway, yeah, it's an interesting question.
Yeah,
We should go back to that.
I see what you mean.
I don't know. Maybe this is wrong. But from the point of view of the field theory, you may be able to get some information like, considering a theory in flat space with a non-trivial, but in a non-Levi-Civita, well, with a connection which is non-Levi-Civita. I don't know what this means. Minkowski space, but non-metric compatible. That does have an additional Gates field. This is, I think, the usual story of Weyl, where you introduce the Gates field like an electromagnetic field, and you have electromagnetism.
Right. That's what we have in the boundary here.
That's what we would have in the boundary. So this could be an original. This should be a new. This should be a new field with its own dynamics, maybe, which is coupled to stuff that are, invariant under this U1, that have U1 charge. But I don't know. So maybe let's put it in this way. Maybe at least to leading order, introducing the Weyl connection is like equivalent considering Einstein-Maxwell in the bulk, something like that. I don't know. Maybe it's not correct, but
yeah, the difference is that it doesn't seem to have dynamics. It's pure gates. There is no F squared for this angle. I think that means something for the boundary fluid, but I don't know.
No,
you have interpretation.
In the boundary, you are not supposed to find the dynamics.
Yeah. In the boundary, it's backgrounds, metric, right?
It's just an asymptotic condition. But I think, maybe we should stop here, because if you couple gravity with a conformally invariant theory like electromagnetism, then you can always somehow decouple them in the bulk, in a space-time. So if you couple gravity to Einstein and your metric, you require that your metric is, for example, conformally flat, then you can always decouple them. They do not couple. So you can talk about the metric independently, but it doesn't care. It doesn't care the metric whether you have the Gates field or not. It's an independent thing. So maybe that's the condition that you put in the bulk. That I have this ambient metric, but it is equivalent to having the ambient metric coupled to something which is conformally flat, the U1 field, and I can always decouple them or something. Anyway, so this we should discuss in private.
Yeah, we can discuss this. Yeah, it's interesting idea. Okay, maybe we should end this unless there are more questions. Thank you for your attention.